I talked about oscillations or vibrations of a single object like a pendulum in which a heavy object is attached to a long string. We treat this heavy object as one object or one particle and do our analysis. I talked about object which is connected to a spring, how that oscillates, that vibrates. I also talked about oscillations of two objects which can interact with each other, like two things connected with some kind of a spring or so. So, that also I showed. Now, today I will be talking about oscillations or vibrations of a large number of, very large number of particles connected with each other. What I have in mind is a solid object, and from there we will understand what the wave is or what the wave motion is, and especially my waves today will be all mechanical waves where particles will contribute. So, let us start with an activity. So, you see here a tumbler and water is filled in it, placed on this table. So, the table is at rest, the tumbler is at rest, the water surface is at rest. At least visibly you see that everything is at rest. Now, look at my hand. I am putting my hand here and doing something on the table, and you look at this surface of water. Do you see some motion on the surface of water? And do you see any motion in my hand? Do you see any motion on the table here? What I am doing? How I am making this water surface to vibrate? Small movement you can see in my hand. I am pressing the table down and then releasing that pressure, and that I am doing very gently. So, I have created some motion here in the particles of this table surface by pressing it down or releasing, and this motion created here is able to cause motion of these water particles. So, how does that information travel from here to here? What has gone from here to here? What has conveyed that information from here to here? Let me do another kind of motion. Look at my finger. Look at my finger. I am moving my finger on the table surface, and you look at the water surface. So, again I am giving some motion to the surface particles, possibly because this is a rigid body, almost a rigid body, a solid body. I cannot move this particle from here to there or there to there. So, very small motion about its own equilibrium position can be created without breaking the table by just moving the finger, but that small motion is able to create a lot of vibrations there. Similarly, if I tap it, my finger, my thumb, you can see the kind of vibrations. So, what we say is something is going from here to there, and what is that going? What is that thing which is going? Nothing is going. The particles which are here remain here, the particles which are here remain here, the particles which are here remain here. Nothing goes from here to here. But the kind of disturbance that I am creating in these particles, they are creating similar disturbances in their neighborhood, particles in their immediate neighborhoods, and then when those particles get disturbed, they give similar disturbance to the next layer in their immediate neighborhood, and this is how the disturbance that we create here, similar disturbance is created here, then here, then here, then here, and reaches the glass tumbler. and then the glass tumbler itself creates disturbance in water, and that creates disturbance at the surface and it vibrates. So, that is what we call wave motion. No particles are going from here to here, but this kind of disturbance that we have created here, the similar disturbance is being created at other positions in this direction down the line. That is what we say a wave is moving in this direction. You can also observe that when I am giving this kind of motion, whatever particles I am trying to drag, that is in left right direction, whereas the wave motion is in perpendicular direction. Similarly, if I am tapping it or I am pressing it, I am giving it a vertical motion, but the wave propagation is in a perpendicular direction. So, you should identify very clearly what is the particle motion and what is the wave motion. The wave motion is created due to particle motion, right, but they are totally different. Wave is no material is moving, wave is a kind of disturbance that you had created here is being created there. So, that is how something we say that something is moving and wave is moving, where particles are the real particles. So, motion of particle, motion of wave, the directions will be different, the magnitudes will be different. Wave goes from here to here 10 centimeters, 15 centimeters, 20 centimeters, particles go probably hardly a micrometer or so. So, these two kinds of motions are to be differentiated. So, we will be doing more activities to see this wave motion. My next demonstration on waves will be on a long spring or the slinky. This is a gift item easily available. You can stretch it to a very long length, and then if you disturb at one part of this long spring, that disturbance travels on this. In fact, we have separately video shooted this disturbance and this wave motion, and I will be discussing on the basis of that video clip. So, what did you see? We created a disturbance at one end of this long spring by shifting some of the coils sideways, and then you saw that as time passed, this disturbance traveled along this spring, reached different places. So, that was the first observation you must have done. Another observation which I am sure you have not missed is that the wave comes back after reaching the other end, the disturbance again comes towards the starting point. One more observation, if you are keen enough, you must have seen that the direction of displacement of the coils. When we started the disturbance, we moved the coils towards right, and as it went from one end to other end, the displacement was always towards right. But while the disturbance was coming back, then the displacement was towards the left. So, we are now running the clip again, and you check that all these observations are there in this motion. So, here we have collected 3 frames of that motion when the wave is going from one end to the other. In the top frame, you are seeing that some of the coils are displaced from their positions, their equilibrium positions, and the rest of the coils are nearly at their own position. As time passes, you can see that these coils which were displaced in the beginning, they are now at rest, and some other coils down the line are now displaced, and similar thing in the later frame, third frame. So, what has moved? What is going from one end to the other end? Wave is going from one end to the other end, but is there any turn, any coil of this long spring is going from one end to the other end? No. Each turn or each coil is only moving a little, it is going sideways and coming back. Nothing is moving from one end to the other end. But yes, the disturbance, the fact that some of the coils are going sideways, this is now happening with different set of coils down the line. So, that is what we know by this wave motion. This is one setup on which we can demonstrate the wave motion, and you can see these are long toothpicks and they are sandwiched between two layers of cellophane tape. One layer is from one side, another layer is from another side, and in between we have put these toothpicks. So, this is a kind of a connected system, and all these toothpicks, individual toothpicks, this you can take as some kind of a particle or some kind of portion of the medium, and these are connected or they can interact with each other through this cellotape which is binding them. So, you can see everything is in roughly in equilibrium position, and the disturbance I will create in one of these straws or at some portion will be an angular displacement from this equilibrium position. So, for example, this particular toothpick, if I pull it in one direction, it will rotate, and that angular displacement will be our disturbance. So, I do this disturbance in this portion, and you see how it travels down the line. So, you can observe wave going from one end to the other end, and then you can also see the reflection as you saw in that long spring, and if you can watch, you can also see the direction of that angular displacement in the ongoing wave and the reflected wave. You have seen several examples of wave motion in which you have some kind of a connected system of connected particles like a solid, like a surface of this table or a spring or maybe a rope, and we created some disturbance locally in some portion of this connected system which we can call medium for wave propagation, and that disturbance which was created at one portion could travel in that medium, in that system, in that object, and could reach somewhere else. Although no particles moved from one place to other place, they were only locally disturbed. So, those kind of wave motions we saw. Now, let me try to write it in a mathematical functional form. When I describe motion of one particle, what do? I ask how much is the displacement at a given time t. Here also I can ask a similar question, how much is the disturbance at a given time t, but then disturbance of which portion. So, I have to specify of this big system which portion I am talking of. To start with, let us talk of a one dimensional system, so that the medium or that object in which the wave is travelling can be described by just one coordinate, like a string. Let us say string. Let us say you just have a string. Of course, the string should be tight and all that. So, some portion you can say that okay, this is x equal to 0 and this is x direction, and then each portion is described by a particular value of x. And then let us say at t equal to 0, this particular portion is disturbed and it is like this. This string is like this. So, the disturbance is here, disturbance is here, disturbance is here, larger disturbance here, smaller disturbance here, and so on. Here the disturbance is 0, here the disturbance is 0. To quantify that, let us say that how much sideways it has gone, we call that as phi. So, this portion of the string has been sideways deflected from here to here, and that deflection, that displacement, I call phi. What will happen after some time? After some time, this disturbance will reach somewhere else. So, let us say it has reached here. I assume that there is no dissipation and the same shape which is here, the same shape is here. So, no dissipation. No dispersion. How dispersion is coming here? This is, what do I mean by saying no dispersion, is that entire wave is going with one particular velocity. This wave moves in positive x direction with fixed velocity v. If it is not, then you can have a change in shape. If the front portion moves with a higher speed and the rear portion moves with a smaller speed, then you will have change in shape and all those things, which that we call dispersion. Let us say this is time t equal to t. Okay, so this is time t and this is time 0. This point is x. So, what is this point? What is the coordinate of this point? Since the wave is moving in positive x direction with velocity v, this distance must be vt. And hence the coordinate here should be x minus vt. So, assuming no change in shape, etc., whatever is the value of phi here, whatever is the value of phi here, okay, whatever be the value of this displacement here, same is the value of phi here. So, if I write this as phi x comma t, if I write this as phi x comma t, why this comma, why these two variables? Left to the comma tells me which portion I am talking of, x, that means I am talking of this position. Right to the comma tells me what time I am talking of. So, at this position x, at this time t, what is phi? So, that is this phi. And for this, what do I write? What do I write? This is phi, which position? This position is x minus vt. So, left to the comma x minus vt and right to the comma time is 0. So, 0, and these two are same under those assumptions. So, this tells us a very interesting fact, that the general expression for disturbance in terms of x and t must have, that expression must have x and t coming only in this combination. X and t must come as a combination x minus vt and nothing else. For example, if I write phi xt is equal to some constant times e to the power some minus x minus vt divided by a whole square, that is okay. This is a good function. It is a valid wave. It is going in x direction with velocity v. But if I say that phi is equal to phi xt is equal to some constant times some x square by say a square plus some v square by some v naught square and times some t square by some t naught square and so on. This is not a wave propagating in positive x direction with velocity v. So, this is not a wave, it must come in this combination. And similarly, if the wave is going in negative x direction, what will happen? If this wave is going in negative x direction with velocity v, this will be phi xt equal to phi or x plus vt0. So, the functional form must have x and t coming in this combination.